An inbound warehouse logistics operation is a high-speed, dynamic physical environment. Semi-trucks back into concrete docks, steel doors roll up, and goods move fast. But every physical movement on that floor must be mirrored by a digital transaction record. If the system updates fall behind the physical pace, the entire facility bottlenecks. Looking at this chart, you can see the baseline organizational layout for managing that tracking. SAP S/4HANA Embedded EWM. Out of the box, SAP provides pre-configured best practices, like Scope Item 1FS, to handle basic inbound processing. Those standard configurations are highly structured, but they can be too rigid to match the actual messy realities of a warehouse floor. You might find missing data at the yard gate, run into strict packaging specification requirements at the receiving dock, or deal with a bloated scanner interface that slows down your forklift operators. Relying entirely on the standard out-of-the-box process creates physical delays. To close the gap, architects have to build surgical, custom extensions into the system. Our objective is to engineer a custom, synchronized inbound pipeline, ensuring that data capture, packing, and put-away move in lockstep with the physical pallet. We will build this using 3 technical pillars: business add-in or BAD-I implementations at the yard, custom data models for the dock, and presentation profile manipulation on the floor. We structure this architecture by following the chronological physical flow of the pallet itself: arrival, then packing, and finally put away. True extensibility in EWM requires aligning the system's logic directly with the physics of your warehouse. We start at the origin point of the inbound flow, the yard gate, where the transportation unit, the truck or trailer, first arrives. The standard EWM process contains a vulnerability here. It does not mandate the capture of a license plate or pager number upon arrival, which immediately breaks tracking and traceability. To fix this, we implement the before-save method of the standard delivery processing body. Here, the first phase of the ABAP logic verifies that the transportation unit's business object state is actively changing. Once confirmed, it evaluates the license plate and pager variables. If empty, the system raises an exception to stop the process. Notice that the message statement here includes the into addition. You have to write it this way to properly display the error context to the user without crashing the entire save sequence. By forcing data validation here at the gate, you secure the origin data point for the rest of the warehouse pipeline. Next, the physical flow moves from the yard gate to the loading dock, where goods are unloaded and need to be digitally packed into handling units. The standard EWM auto-packing process relies on highly complex packaging specifications, or unified package builders, to determine how items should be grouped. If your warehouse only maintains simple unit-of-measure quantity classifications, like pieces, cartons, or pallets, the standard auto-packing will fail to create the handling units. We can build a leaner alternative by mapping those unit-of-measure quantity classifications directly to packaging materials. This custom master data table, created in the ABAP dictionary, holds that exact mapping. Fields within this table, specifically QuanCla and PackMat, bridge the gap between abstract quantities and the physical box types used on the floor. For example, if a product arrives with 400 individual items, the system identifies that a grouping of 192 items equals 1 pallet. That quantity gets assigned classification P, which routes through our custom table and outputs the requirement for a standard wood pallet handling unit. Creating custom intermediary database tables lets you bypass rigid standard requirements and operate with a highly resilient data model. With the custom table built, we now have to instruct the system to actually use it during the creation of an inbound delivery. We do this by implementing the HU_proposal method of the AutoPack BAD-I. In this implementation snippet, the first logical loop iterates over all delivery items, fetching the quantity classification based on the unpacked quantity. The code uses that classification to query our new table, finding the exact packaging material required for those items. Finally, the execution phase determines the target quantity, creates the new handling unit, and virtually packs the delivery item into it. There is a critical technical constraint within this specific BAD-I environment that you need to watch out for. You must never use save or commit work statements here. The calling environment assumes complete responsibility for saving and handling database commits. This implementation operates as an invisible engine on the dock, instantly translating raw inbound numbers into physical handling units without requiring a single human click. The goods are now packed, and we shift our focus from the dock to the warehouse floor. A forklift operator needs to move those units to their final storage bin using an RF scanner. Standard RF logic often creates friction here. The default put-away transaction forces the operator to scan a confirmation at the source bin on the dock, and then scan a second time at the destination bin in the racks. If a pallet is moving directly from the receiving dock straight to the rack, that source bin confirmation is a redundant, time-wasting step. We fix this by modifying the RF presentation profiles, but you should never alter the standard fallback profile directly. Instead, copy the standard presentation profile to a new warehouse-specific profile. In this diagram of the standard 4-step flow, we modify the logical transaction by changing the source step PTH-USC to run in the background. For the operator, the scanner completely skips the source screen and immediately displays the destination requirement. Bypassing this redundant screen significantly reduces cumulative friction for every pallet, allowing the system to keep pace with the actual speed of the forklift operators. Let's track the physical journey of the pallet one last time, now running on the custom digital pipeline we constructed. At the yard, we enforced data validation, blocking incomplete records at the perimeter before they could enter the system. On the dock, we bypassed rigid configurations, dynamically generating handling units using custom tables and targeted ABAP methods. And on the floor, we eliminated interface friction by overriding the RF presentation profiles, letting the operator work without interruption. Mastering SAP S/4HANA EWM architecture means surgically applying frameworks so the digital system becomes invisible to the physical worker.